All the problems on this worksheet involve a concept called stoichiometry. In a stoichiometry problem, we are given an amount, a quantity of one particular molecule, and we are asked to convert into a different molecule. So for this problem, we're being given the quantity 16 moles of H2, and we're being asked to use that information to convert into moles of NH3. All stoichiometry problems require that we use a balanced chemical equation. So the very first thing we're going to do is balance this chemical equation. 2 nitrogen on the left, we need 2 nitrogen on the right, and we have 6 hydrogen on the right, so that means we need 6 hydrogen on the left, so that makes this equation balanced. Stoichiometry problems, even though a lot of students have a lot of anxiety about them, they are just unit conversion problems. Like literally that's all that they are. We're going to treat it exactly like it is, meaning that we're going to treat it like a unit conversion problem, and that means step 1 is to write the number and the unit that has been provided to us. The problem has told us that we are starting with 16 moles of H2. So we're going to start by writing that out, and then just like any unit conversion problem, the next thing we want to do is multiply by a conversion factor that allows us to cancel out that unwanted unit. The unwanted unit is moles of H2, so we're going to put that at the bottom of this conversion factor, and we want to convert into our desired unit, which is moles of NH3, so that's going to go up on top. In this conversion factor, we're going to fill this in using the stoichiometric coefficients from the balanced equation. So when we balance the equation, we saw that the coefficient for NH3 is 2, so that's going to go here, 2 moles of NH3, and the H2 coefficient is a 3, so that's going to go right here. The stoichiometric coefficient gives us the relationship between NH3 and H2. So the way that we have this set up, the moles of H2 are canceling, and this leaves us with 10.7 moles of NH3. So let's move on to our next one. For this one, we have been told that we have 5 moles of KClO3, and we're being asked to figure out how many grams of O2. So we're converting from moles of KClO3 into grams of O2. And first thing we need is a balanced chemical equation. This one's actually a little bit trickier than the first one, so I'm going to use this strategy of writing all the different atoms down and keeping track of how many of each type we have. Currently, on the left-hand side, we have 1 potassium, 1 chlorine, and 3 oxygen. And on the right-hand side, 1 potassium, 1 chlorine, 2 oxygen. So our potassiums and our chlorines are balanced, and we need to balance the oxygens. This is that interfering coefficient scenario where it's going to take us a couple of iterations to get the oxygens balanced. We need more oxygens on the right hand side, so we'll change that coefficient from 1 to 2, which gives us 4 oxygen on the right. Now we need more oxygen on the left, so we'll change this coefficient from 1 to 2. That's going to change the quantity of everything, and depending on how comfortable you are with balancing equations, you may be able to go straight to the correct coefficient and not do this iterative process like I am doing. I'm going to keep working on the oxygen even though we've unbalanced the potassium and the chlorine. We need 6 oxygen on the right hand side, so we'll put a 3 there, that gives us 6, and then we need a 2 here for the potassium and the chlorine so that we've got 2 of each of those. And now it's balanced. And now we're ready to actually work on the stoichiometry part of the problem. Again, we want to start by writing the number and the unit that was given to us in the problem. That is 5.0 moles of KClO3. And then next we want to multiply by a conversion factor that puts the moles of KClO3 down on the bottom because we're trying to get rid of those. And we need to convert into the problem, like ultimately we want to convert into grams of O2. However, there is this rule in stoichiometry that when you are converting from one type of molecule to another type of molecule, like from H2 to NH3 or from O2 to ClO3 or whatever, you're only allowed to do that in a mole to mole conversion. So even though ultimately we want to get to grams of O2, we're not able to do that yet. Again, if we're converting from KClO3 into a different molecule like O2, we have to do that in a mole to mole conversion, where in the conversion factor we have units of moles on the top and the bottom. And remember that this part of the conversion factor is coming from the coefficients in the balanced chemical equation. 3 moles of O2 and 2 moles of KClO3 because those are the stoichiometric coefficients. And that will get rid of our moles of KClO3. Now again, that's not the unit that we want, so we need another conversion factor here because moles of O2 is not our desired unit, so we need that unit to go away. What we're trying to figure out are the grams of O2. And converting between grams and moles of a molecule, like converting between grams of O2 and moles of O2, that's something that we've practiced for a while, so we know how to do that. This is coming from the molecular weight of O2, looking at a periodic table. The mass of oxygen is 15.999, and the mass of a second oxygen is the same. That's going to give us a total mass of 32 grams per mole for the O2 molecule. And that will let us cancel out that mole of O2 unit, and we will be left with units of grams of O2. 5 times 3 divided by 2 times 32 is 240 grams of O2. If I'm paying attention to sig figs, I shouldn't have that decimal place there. So let's take a look at this next one. This next one, we are starting with 0.75 grams of sodium hydroxide, NaOH, and we're being asked to convert that into moles of H2O. Let's begin by balancing our chemical equation. Sodium, we have 1 on the left and 2 on the right, so let's put a 2 right here. Oxygen, we have 1, 2 on the left, plus another 4, so that's 6 on the left. And we have 1, 2, 3, 4, 5 on the right. But since we have oxygen in a couple of places, I kind of don't want to mess with it right now, so let's leave that alone. Hydrogen we also have in a couple of places. Let's leave that alone. Maybe we're going to have to address it. I think we will. Okay, so we've got 6 oxygen on the left, and we have 1, 2, 3, 4, 5 on the right. I'm going to put a 2 here. That is going to give me 1, 2 plus 4 is 6, and 4 plus 2 is 6 for my oxygen. I have oh, here we go. I was losing hydrogens. I have 2 hydrogens here plus another 2 hydrogens here. That's a total of 4. I've got 4 hydrogen atoms right here, 1 sulfur and 1 sulfur. So this is balanced. And whenever I have blank lines in a balanced equation, I always like to write in the ones, even though we normally wouldn't write the ones in. That's just kind of a quirk of mine. So we're going to start by writing the number and the unit that has been provided to us in the problem. We have been provided with 0.75 grams of NaOH. And we need to multiply by a conversion factor that allows us to get rid of that unit, grams of NaOH. Notice that I'm not even at this point thinking about what I'm trying to convert into. I just know that I need to get rid of the grams of NaOH. Now, when we are in units of grams for a particular molecule, we only have one option in terms of what we can convert it into, and that only option is moles of that same molecule. So this is a really important stoichiometry rule. Whenever you're in grams of any particular thing, whether we're talking about at the beginning of the problem or maybe we're somewhere in the middle of the problem, whenever you're in units of grams and you're trying to cancel that out, the only thing that you can convert grams into is moles of that exact same substance. That's your only option. So the only thing we're able to do is convert the grams of NaOH into moles of NaOH. And again, we do that using the molecular weight of NaOH. Na is about 23, oxygen is about 16, and hydrogen is 1. So this is going to be 40 grams, roughly 40 grams per mole of NaOH, and that will cancel that unit. We're not trying to figure out how many moles of NaOH, we're trying to figure out how many moles of H2O, which means we need another conversion factor, and in this new conversion factor, we need moles of NaOH down on the bottom, so they cancel, and we need moles of H2O on top, because that is our goal. When we're in units of moles of one molecule, like NaOH, we are able to convert into moles of anything else that we want, as long as they are connected by a balanced chemical equation. Using the stoichiometric coefficients from the balanced equation, 2 moles of NaOH, 2 moles of H2O, again, that comes from the balanced equation, and those mole units are going to cancel out, and this is going to leave us with the correct units, which is moles of H2O. 0.75 divided by 40 times 2 divided by 2, which I'm not going to do in my calculator, that gives us 0.01875 definitely not to the right number of sig figs, but whatever. We've got one more of these problems that we can practice on. Let's take a look at balancing this equation. We have 1 carbon, 1 carbon. We have 4 hydrogen, so we need 4 hydrogen over here. We have 2 bromine. We have 1, 2, 3, 4, 5, 6, 7, 8 bromine, so we need to have a total of 8 bromine. So this is asking us to convert from 4.5 grams of CBr4 into grams of CH4. We're going to start by writing the number and the unit that has been given to us in the problem, 4.5 grams of CBr4. We need to multiply that by a conversion factor, put that unwanted unit, grams of CBr4, that unwanted unit goes down on the bottom. Remember, in this problem up here, I told you, when you're trying to get rid of grams of anything, it doesn't matter what it is, if you're trying to get rid of grams, the only thing you can do is convert into moles of that exact same molecule. So our only option here is to go from grams of CBr4 into moles of CBr4 using the atomic masses. Carbon is roughly 12, bromine is roughly 80, and there are 4 bromines in this molecule. 80 times 4 plus 12 is a molecular weight of 332. And that lets us cancel out that grams of CBr4 unit. Now we can work on getting rid of the moles of CBr4. Now if we're in units of moles and we're trying to convert to get rid of that unit, we can convert into moles of any other molecule that we want, as long as it's in this equation. So now is when we want to look at, what is this problem asking us to do? What are we trying to solve for? CH4, that means we want to convert into moles of CH4. And we're going to do this using the stoichiometric coefficients from the balanced equation. The moles of CH4 has a coefficient of 1, and the moles of CBr4 also has a coefficient of 1. So mathematically, we're not doing anything in that step. That's not always the case. Don't assume it's always going to be like that. Now this still isn't what we're trying to figure out. We're not trying to figure out moles, we're trying to figure out grams, so we need another conversion factor that has moles of CH4 on the bottom. And remember, I've told you this is the 3rd time now, when you're trying to get rid of units of moles of anything, your only option is to convert into grams of that particular thing. Actually, I said that completely backwards from how I've said it before, even though what I just said was accurate. That isn't the 3rd time I've said that. So we are going to use the molecular weight for this. Carbon is 12, hydrogen, each one is about 1, and there are 4 of them, so that gives us a molecular weight of 16 grams per mole, and those mole units cancel, and we're going to be left with units of grams of CH4. 4.5 divided by 332 times 16, because I'm not going to do times 1 divided by 1, that's going to be 0.22 grams of CH4.